everybody. In this video, we will discuss the principle of least action and Euler-Lagrange equations. The main goals of this, may I call it a lecture, is to provide some insights and intuitive understanding of this principle and the use of functionals and functional derivatives to a specific and relevant problem. Okay? So let me start by using some analogies in order to discuss this. So an analogy from calculus, from ordinary calculus, okay? It comes from ordinary calculus, okay? Suppose you have at first a rectangle which has sides x and y, and the total perimeter x plus y, twice of that because you have x here and x here plus y and y here, equals to 4L, some fixed quantity. So this is a constraint. The perimeter is constrained, okay? You cannot exceed 4L. As a matter of fact, the perimeter of this problem must be exactly equal to 4 times this quantity L here, which is a length, suppose. Okay? And of course, you can calculate the area of this, let me call it A, the total area of this object here, which, as we know, corresponds to the product x times y. All right, this is just the area of a rectangle of a simple geometric figure. But if I use this constraint here, because the perimeter is constrained, I can rewrite the variable y, which is one of the sides or two of the sides of this rectangle. I can rewrite it as a function of x, because I can only change the values of x and y, but the sum of both must be twice this value of L. Okay, I can divide by 2 here. So I would have here for this equation x plus y equals to twice L, twice the value of L. And of course, I can rewrite y as a function of this x. X or 2L minus x, 2L minus x is equal to y. All right? So the problem is the area here corresponds to x times 2L minus x. And suppose you have these sides of this rectangle adjustable, you can adjust that, but remaining fixed the perimeter of this geometric figure, and you want to maximize the area of this figure. I can find a value for x, which implies a value for y, all right? Keeping the perimeter, the total length of the sides, the sum of the lengths of the sides, a constant. But I want to maximize the area. So, suppose in doing that, you could try it by changing the sides, trial and error, and you could make y very small and x is nearly equal to L, all right? Or so this is small y, and huge value for x, or you can do a greater y, diminishing a little bit the x value, and of course you can change the values of x and y until you reach the maximum area, okay? So you could plot this area as a function of the value of x, which can go from 0. So if you have 0 for x, the length is completely described by it's just twice the y is equal to 4l, right? Or you can make y equal to 0, so you can change, and in the end you can plot this area as a function of x, all right, as a function of this variable. So this is a, which is the area. You could think it is a cost function, okay? It's some kind of cost, all right? You can change x. It is a function now of x. It's a function of x. You can change the value of x, and in the end, you'll change the total value of the area. So this is a parabola, okay? It is twice the value of L times x minus x squared, all right? If you plug in here x equal to 0, produces a 0 value for the area. And of course, this grows until it reaches a maximum and then goes to 0 again, right? So, because this is the problem, all right? If you pick up x value equals to twice L, 2L here, you'll find 4L squared minus 4L squared, it goes to 0. So this is 0 for x, this is twice the value of L, which would correspond to y equals to 0, okay? So you're making your rectangle approaching just a straight line, right? So this has an area of 0. And there is a maximum here. There is a maximum area, which I will call A0. And I want to know what is this value of x here, which maximizes, in this case maximizes, but in other circumstances, I would prefer to minimize some function, okay? So, but in this case, maximizes the value of a, which is our cost function. It maximizes this. What is this value? What we need to do to find out at what value of x this maximum allowed area occurs, okay? So we know from ordinary calculus, from elementary calculus, that we can calculate the derivative, and derivative here with respect to the variable x is equal to 0, all right? So at this point here, at the maximum, at the value of x, which extremizes the area, in this case maximizes the area, the derivative must be set to 0, because the derivative corresponds to the tangent to the curve, and in this point here, at this point here, it is 0. So we can find it, just calculate the derivative here, and we have twice L minus 2 times x equals to 0. It's just calculating the derivative of this function, and we'll find out that x must be equal to L. So the answer to this question is x equals to L. And in this case, y is also equal to L, and the maximum of the area, if you keep the perimeter of this geometrical figure a constant, you cannot change, it's a constraint to the problem. The maximum area is when you reshape this rectangle to a square with sides of length L, which makes a total perimeter, a sum of the sides equals to 4L. Okay, so this problem is a problem of optimization. Okay, you have a cost function and you need to optimize. You need, in this case, to maximize the area. All right. So the principle of least action is somehow related to that. So you need to define an action in physics. Okay. So in our main subject here, which is the description of a physical system, you have a cost function. Our cost function is usually called an action. The action, right? The action is a functional, which is a functional. In the case of our analogy, the problem is related to a function, which is the area. Our cost function was the area, and the area was dependent on a single variable x, all right? But in our problem, in a general problem in physics, we perhaps have the dependence of this cost function in a set of parameters, or perhaps depending on something like the trajectory of the particle, right? So the action is a functional. It is in my terminology, it's a function which has as its argument a infinite dimensional object, which is a function, right? And for a function, I could interpret each component of the function, the value of the function at some point x in space, as a component of a vector in an infinite dimensional space with a continuous set of orthogonal vectors, right? So suppose in a straight line x, you would have an infinite set of points. For each point, you could introduce a vector which is completely orthogonal to some point x prime. So this is some x, this is some x prime, and you have x projected onto x prime would be a Dirac delta, right? So our action would depend on the values of a function. So a wave function or something else would depend. It could be time, of course. It could depend on all the possible values at each point, all right? But the action in physics, it is written, the action is written this way. Usually the symbol for that is A or S, all right? The capital A or the capital S, right? I'll use A here to remember action and to make it more closely related to our analogy. So A, which is our action, it can depend on some function. Usually we use Q for denote coordinates, which depend on T. I will use T prime here. All right, T prime. So Q of T prime is a coordinate And q dot, depending on t prime, is just the derivative of q with respect to t prime and the value of t, and it is a velocity. Of course, this could be a vector, so this is a velocity vector, and I could write it as a q some subindex y to denote the component and the velocity some y. Okay, well, but I will drop out the indices to make it simple, to make it more easy, make it easier to understand here. So we have a coordinate and the velocity which corresponds to the derivative of this coordinate. They are both independent. They are independent variables. Okay, so they are independent. And the action in physics is defined as an integral of a function which is called the Lagrangian of your problem. In that case, we are trying to we were trying to calculate the area, and we don't have we don't have in that problem a time coordinate, so the integration disappears in that analogous problem, right? But you have a cost function, the Lagrangian there, and the Lagrangian in the previous problem was just x times 2l minus x, just something like that. Okay, our coordinate was in that problem x. All right, I'm using q here. So the Lagrangian depend on the vector q, or in the components of the coordinate. So I'm using just a single coordinate. Suppose the space is one dimensional here, which depend on t prime. The Lagrangian should depend on the velocity q dot of t prime, all right? And it is integrated over the entire domain of time, all right? I was forgetting to mention that t prime is time. The time, or the parameter, or the variable which parameterizes the trajectories of q and q dot, all right? So it is time for us here. Okay, it could be another variable in another circumstances. So you need to integrate here from t naught, or t0, which is the initial instant of time, to the final time, t final. And it corresponds to a trajectory from a initial point to a final point in space. There is a trajectory here, right? A particle, suppose it could be a particle. It is moving from q naught to q sub f to a final position here. Could be vectors here, okay? In general, it could be vectors, right? And at each point here, you have a q dot, a velocity, which is tangent to the trajectory here as a function of t prime, right? So here you have another value of the velocity, but the constraints to this problem here, which analogously you would have as a total perimeter in the analogous problem which we dealt with, corresponds to the initial and final states. All right, so there are constraints here. Constraints you cannot change it. You need to fix this point and this point. The initial and the final points of the trajectory are Q naught, which is the Q of t0, Q final, which is the value of the coordinate at the final time. It's the end point. This is the initial point. This is the end point. All right. And you have this as constraints. You cannot change these points. They are your constraints in your problem. Okay. So the action acts as a cost function. All right. The action is your cost function. This L here, this function, I mentioned that, but it's worth of writing here. This is called the Lagrangian function. It is a classical function in this problem. All right, it's a classical function which depends on the coordinates and the velocity and the velocities. Okay, because if you are dealing with more than just a single space dimension, it could be a vector here, it could be a vector here, and you constrain the initial point, the vector, and the final point is a vector. Of course, the velocities here and here also are constrained. Okay, you're supposed to know these velocities at the initial and at the end points. Okay, you know that, right? So this is our cost function. But now, what is the problem? Nature has chosen a way to work, and this way corresponds to, well, first, what question I should ask here? What is the actual trajectory from going to the initial to the end point? It could be a straight line, it could be a wavy line, I don't know. What is the trajectory which actually occurs for a, in this case, a particle going from this point to that point, from A to B? What is the trajectory? So the problem is find the trajectory. Q of t, and of course the velocity would be defined q dot of t with constraints q naught and q final. These are fixed. The initial and end point are fixed. Find these trajectories, okay, or find the most probable trajectory in quantum mechanics, or find the exact trajectory from going from A to B in classical mechanics. How can I define, or how can I calculate this trajectory? So in order to find this trajectory, the answer is nature has chosen that way. The trajectory is the actual trajectory. Let me rewrite it. The actual trajectory is that one which extremizes the action integral. Since an integral is a functional, the action is a functional which has as its input the coordinates of the particle and the velocities, of course, the velocities. And The actual trajectory is the one which extremizes, which maximizes for some types of problems. In the case of the area, in the previous example, you need to maximize. In some other problems, you need to minimize. So we will write it as extremizes the action integral. Okay. So how can I find the, the actual trajectory? I need to calculate the maximum or the minimum of this function, the extremum, the extremal value of that function, the action. Okay, I need to extremize that. And how do we proceed in ordinary calculus to do that? We calculate the derivative. In this problem, we need to calculate. How can we do that? We need to calculate the functional derivative. So how to do that? Calculate functional derivative and equals it to zero and make it equal to zero. Equalize it to zero. Because in a maximum or a minimum, you know that the tangent or the derivative vanishes. Okay, vanishes. Right? So let us calculate the functional derivative. But now the question is, with respect to what we need to calculate the functional derivative? So remember, in the previous problem, the area was a function of x, a single variable, a single independent variable, which after extremization we will assume a single value. Here I need to find out the trajectory. I need to find out the values of q at each instant of time. Time is a continuous, so time indexes the point in the trajectory. So if you discretize the trajectory, let me erase a little bit here. If you discretize the trajectory from Q naught to the Q final here, Q final, you could discretize it. You would have a Q1, Q2, Q3, Q4, Q5, and so on. And you need to find out the value, not for the initial and endpoints, they are constraints. Okay, they cannot be changed. But you need to find a specific value for Q1, for Q2, for Q3, Q4, Q5, and so on and so forth. And in the limit where you this is at time t1, t2, t3, t4, t0, the end, the final time here, the final. If you in replacement of a discrete delta t, you take the limit delta t going to zero. In the limit delta t going to zero, this becomes a continuous trajectory reaching the endpoint here, okay, at the final time tf, okay, at the final time tf. So it is a multivariate calculus which I need to employ. And in this case, the functional derivative, because there are an infinite set of values here, q between q naught and q1, you have an infinite set of another values, all right? And between q1 and q2, another infinite set of values for this function, which becomes, in the limit delta t going to zero, a function q of t. So this is the variable which I need to use to calculate the functional derivative. I need to calculate the variation of the action with respect to the trajectory q of t and equalize it to 0. This is what I need to do, right? I don't know if you are understanding what I'm trying to say here, but in the previous case, the area is a function of just a single x, all right? So it was x 2l minus x, and we calculate a derivative of a with respect to x, equalize it to 0. Put it equal to 0. It needs to vanish. The derivative needs to vanish in order for us to find out what is the extremum of that function, all right? But here, our action, if you discretize it, it becomes a sum over J of the Lagrangian, depending on the coordinate Q at the time Tj and the velocity Q dot at that time Tj. You need to sum over. And of course, you need to multiply it by the step delta t. All right? This action, as a matter of fact, becomes a function which depends on the values, the possible values of q1, q2, q3, and so on, and of course the dot q1, dot q2, and so on. So it depends on multiple variables. It depends on the vector, but not the three-dimensional vector, which could be, suppose, a q vector, which is just the components x, y, and z of the coordinate system in a Cartesian coordinate system. No, I'm saying, suppose you have a one-dimensional world. You have just x. Your q is x, one-dimensional world, and you discretize it. You have the possibles x1, x2, and so on. And at each instant of time, the particle should be in some of that allowed points in your line here, in the line here, right? So the vector I am saying here is the possible values for the coordinate x to be in the instant of time t1, the instant of time t2, and so on. All right. So you have a function of a, in principle, discrete set of variables q1, q2, q3, and so on, and you need to calculate the derivative with respect to each one of these q's and equal to 0. So you will find out a set of equations which will produce for you the trajectory, the correct trajectory. But in the limit, when we take the limit delta t going to 0, this becomes a function, and this becomes a functional because from q1 to q2 there are many other variables in between. It becomes a continuous parameter, it becomes a continuous variable, and you have a functional. So you need to calculate a functional derivative here. A functional derivative and make it vanish because you want to extremize the cost function, which is the, the action, in order to find the actual trajectory of your particle. So it's, in some sense, it is an optimization problem, okay? You need to extremize the action, right? Well, so in classical mechanics, for a particle, we know that the Lagrangian corresponds to the kinetic energy. Let me write is a K minus a potential energy. Okay, so kinetic. So this is the difference between the kinetic and the potential energy. So it is measured in units of energy, in joules, using the International System of Units, or SI. It is measured in joules. All right. So if you have a, suppose, non-relativistic particle, usually this L would be the mass of the particle times q dot squared divided by 2. This is the kinetic energy. Mass times velocity squared divided by 2. It's kinetic energy. Minus the potential energy, which depend on the coordinates. For a single coordinate q, or if you have a vector in 3 dimensions, you have a potential energy which depend on q. It could be dependent on electromagnetic potentials and so on, but this is it. In the case of a usual problem, a non-relativistic particle in classical mechanics, you have a function of q and q dot, okay, vectors in three-dimensional space. They depend on the parameter time. They depend on time, okay, and of course there is a factor which depends only on velocity, and the potential energy which depends only on the position. Okay, kinetic energy depends only on velocity of the particle, and the potential energy depends usually only on the coordinates of the particle. But there are exceptions. For instance, the coupling between a particle with electromagnetic field would have a component which is the coupling between the velocity of the particle and the magnetic vector potential. So it could depend also on the velocity of the particle. This potential energy could depend also on the velocity of the particle. All right. But this is it. You have a kinetic term and a potential factor here. Okay. Usually, let me write it just this way. So you can have a factor which depends on velocity and another factor which depends on position. It will be the case for a particle in the presence of a Coulomb potential or some electrostatic potential, and you are neglecting relativistic effects and corrections due to magnetic fields and so on. Right? So this will be the form of a Lagrangian. But remember, it's a kinetic term minus a potential term, and we'll discuss it a little bit later about how to write this for fields, not for a particle. So here I'm trying to make it simple in order to make it easier for the understanding of the concepts here. All right. But well, let us so write the action, which is a functional depending on a trajectory here, a function of time of another variable. Notice that T1, T2, and T3, and so on in the discrete scenario indexes this, let me say, a vector. And in the end, when you take the limit delta t going to 0, this becomes a function depending on the time, on the parameter time. Okay, so this is an integral from t0 to the t sub f, the final time. It depends on q. Let me write it as a function of t prime, q dot depending on t prime. Okay, so this is the Lagrangian integrated over all the time dt, right? it is a curious fact that a particle in going from T naught to T final, it chooses a trajectory which in the middle of the trajectory it perhaps should not know what would be the final position, but it chooses the trajectory which will lead the particle to that position, right? So it seems uh, it seems weird because for Newtonian mechanics and all the equations we know, they are local equations and usually written in terms of differential equations, which we will find out it will be the result, it is the result of extremizing the action, okay? So what we need to do, we need to extremize this action, always remembering the constraints. I cannot variate the end points, okay? The initial and the end point. I cannot variate that. So I am calculating the functional derivative with respect to this, right? And now we use the definition. Remember definition of a functional derivative with respect to some phi. Okay, this depends on phi, and we need to take the limit where epsilon goes to 0, 1 over epsilon, the functional calculated at phi plus some delta phi, which we write as a Dirac delta function, right? Minus the original functional, and this is divided by this epsilon. In the end, we take the limit epsilon going to 0. In this case, we need to calculate the limit epsilon going to 0, epsilon tending to 0, and our variable here is q. I need to remember that this is calculated at some y value, and this functional can be internally indexed by x. Here it's t prime. So our x in this calculation is t prime, and our y in this calculation is t. Okay, so we'll have to in 1 over epsilon. Here I'll put in front of all the expression. We have to calculate an integral from t naught to the final time, the Lagrangian, which is our function, which is calculated at q at t prime plus epsilon delta of t prime minus t. I am variating the value of q at some instant t in the middle of the trajectory, all right? Of course, I need to calculate the time derivative. In this case, is a total derivative because I'm considering just time as a possible variable. For fields, you have t, x, y, and z, perhaps. We'll see that later. So you have q dot here, which is the derivative with respect to t prime, because variables depend on t prime. Q of t prime plus epsilon delta of t prime minus t, right? So this is the Lagrangian evaluated at q plus some delta q. This is the delta q, okay? And the derivative of q plus delta q, right? This is it. So we close this round bracket here, dt prime, and you need or we need to subtract the original. Okay, so we are just using this definition here now, understanding what the variables are. All right, this is it. Now notice, if I have a Lagrangian calculated at some displacement delta q, and also for the velocity some delta q dot, I could expand it in a Taylor series for multiple variables, of course, and we will have the function evaluated at the original points plus delta q dl dq plus delta q dot dl dq dot. All right, plus higher orders of delta q squared, delta q dot, and so on and so forth, and higher orders. Okay, higher orders. But remember, this delta q depends on epsilon. Epsilon will go to 0, it divides by epsilon. But higher order terms in epsilon will become 0 when we take the limit. So we don't need to go further. We just need the first order in delta q and delta q dot. Okay? And remember the following fact. Delta q dot corresponds to the time derivative of this minus the time derivative of this. So this is q dot plus delta q dot. Sorry, this is the new q dot new minus the old q. And this is just epsilon, the derivative with respect to t prime of the Dirac delta. Okay, because this is delta q. Okay, so this is delta q dot, which enters right here. Okay, I don't know if you are seeing properly, but this is an L for Lagrangian. Okay, and now we can rewrite this delta A over delta Q as the limit of epsilon going to 0, 1 over epsilon. All the factors are integrated over dt, so I could write this integral in front of everything, and we'll have L of Q and Q dot calculated at t prime. I am expanding this around the value of the function at Q and Q dot with small contributions from the variations. Okay, so we have this factor plus delta Q is epsilon delta, the Dirac delta of t prime minus t, so delta of t prime minus t, and the derivative of the Lagrangian is evaluated with respect to t prime, of course, because these are evaluated at t prime, this is t prime, this is, okay, so this is it. Plus another factor here, plus epsilon, the time derivative with respect to t prime, delta of t prime minus t, because of this delta q dot here, which is the variation of the velocity along the trajectory of the particle, times dl the q dot. This q dot is calculated at t prime, okay? So I am calculating the derivative of a Dirac delta function here, and this multiplies dl dq dot. So we have all the factors plus order of epsilon squared, but as I said previously, because it is divided by epsilon, all the factors which are higher order in epsilon will go to zero in the limit. All right, so I don't need to write them anymore. And this is for this factor here minus L evaluated at t prime, the original Lagrangian evaluated at t prime. Now I can close these squared brackets and integrate over the variable t prime, right? This is it. I hope you can see what we did here. Now, notice this factor cancels out this one, and 1 over epsilon times epsilon cancel out, of course. So all the epsilon factors are canceled. So I don't need the limit anymore because it's the limit of a constant with respect to the variable epsilon. So it produces an integral from t naught to t final delta of t prime minus t dl dq evaluated at t prime integrated over dt prime. This is for this factor here, okay? But there is another factor plus integral from t naught to the t final, the derivative, the time derivative of Dirac delta, okay, the derivative times dl dq dot evaluated at t prime and integrated over dt prime here. First term is easy to solve because the variation must be introduced at some point at any value of t which cannot be t0 or t final. The variation of the field only can be made in between these 2 points, the endpoints, because they are fixed, they are constraints. I cannot variate this, I cannot variate this, I cannot variate the endpoints. I can only variate the trajectory here inside, in between these endpoints, okay? So in this case, this time, this instant here, this time here, must be set in order to be anything between T0 and TF, but not T0 or TF, because if you make T equals to T0 or TF, you are making changes here at the endpoints, and the endpoints are fixed. You cannot change that, all right? So this integral is easy to do because when you integrate a Dirac delta function, suppose for a variable alpha minus alpha naught times any function of alpha integrated over alpha in the limits from a to b such that alpha naught is contained inside these limits here, you'll find out that the function needs to be evaluated at the point where the argument vanishes. So alpha minus alpha naught equals to 0 corresponds to alpha equals alpha naught. I just need to replace here f of alpha naught. No problem with that. And okay, the first term I can integrate easily. Just replace where I find t prime by t. So I have dl dq evaluated at time t. So this Lagrangian is calculated at time t, of course, right? As a function of q and q dot, q and q dot at time t. Now, it was q of t prime, q dot at t prime. Now I need to insert in replacement the value of t. But this second integral has a product here, has a product, and I can use a little a trick as a matter of fact. So this is dA dq evaluated at time t. I can use a trick and integrate it by parts. So this factor here, I can rewrite it as a derivative with respect to t prime of a product. Okay, so the product of these two factors minus this delta function and the time derivative of the second one. Okay, so this is what we have for this factor here. We can use integration by parts, or we can use the identity, which says that the derivative of a product minus one of the terms, the derivative of the second, equals the derivative of the first times the second factor. And the second factor is already a derivative of the Lagrangian with respect to the velocity. Okay. So here, the integral of a derivative corresponds to the function. All right. So in this case, this second factor here produces plus integrating over dt. This makes delta times dl dq dot, delta t prime minus t dl dq dot. Okay, evaluated at t prime, but I need, since this is a definite integral, I need to evaluate this factor at the endpoints. And minus the integral of this factor here, but the delta just replaces t prime by t in the other. This is calculated as a derivative of t prime. So in the end, I need to replace t prime by t. Here would be calculated at t prime. This delta enforces it should be equal to t. So I have this one minus the derivative with respect to time dl dq dot calculated now at time t. All right. And remember, I cannot change the endpoints, so this delta cannot be made to work at t naught and tf. This t here never is equal to t sub 0 or tf. Okay, so this delta vanishes because t prime is never equal to t0 or is never equal to t final. So this goes to 0. Okay, the constraints make impossible to change the endpoints or the initial and the endpoint here. So this integral, which depends on the boundaries of your problem, t0 or tf, vanishes. And this integral, all this integral here, all this factor here, all this integral becomes this factor here. Okay? And of course, we need to make it equal to 0. We need to make it to vanish. So the variation of the action, variation of the action, produces an equation which is the so-called Euler-Lagrange, the Euler-Lagrange equation, or equations because in general you have a set of equations because you have a set of parameters here. So if you have a three-dimensional space, for each component I, you have an equation, right? So for each component x, y, and z, dl dx, ddt, the component of velocity with respect to the x-axis, and so on. So this is the Euler-Lagrange equations. Because usually you have more than one function here, right? So if you look at the phase space, you have a q and a q dot in phase space, okay, parameterized by the time t. You have an initial point and an end point, and there are many possible trajectories in principle, of course. Okay, so there are too many trajectories in phase space, suppose. But the one which will be chosen by nature is the one which extremizes the action integral. Okay, the one, I don't know which path the particle will follow, but it is the one which satisfies this equation here, or these equations in the case you have more components for your coordinates. Okay, you can have many particles, so you have the action depending on the coordinates of the particle 1, which is a vector, a particle 2, which is a vector, a particle n, which is a vector, and so on. So for each particle, the derivatives with respect to q of the nth particle and the ith component should be 0. You have a set of equations. Solving these equations will provide you with the trajectory from going from going foregoing from A to B in the phase space here. Okay, this is a phase space. So if we consider the Lagrangian to be an example, a simple example, particle in one dimension in a gravitational field. Is very small gravitational field, not a very weak gravitational field. The Lagrangian would be written as m q dot. Suppose this is the z-axis here. Okay, this is the x-axis, but the particle just is allowed to move in the vertical axis here. The particle has a probability or perhaps a tendency to go downwards because of a gravitational field. There is a force here, which is the wave force, which corresponds to mg in the direction of z, in the negative sense of that axis. And the particle just is confined to move in the z direction. So in this case, I could write this coordinate as z. So I have mz dot squared divided by 2, because velocity of the particle, the velocity of the particle is z dot, is the derivative of the coordinate z with respect to time. Particle cannot move along the x or the y axis. It cannot move in the other directions. So it's effectively confined to a one dimension in a gravitational field. There is a potential energy. The higher the z, the higher the potential energy. Okay, so the higher the z, higher the potential energy. And you'll have this Lagrangian. If we apply Euler-Lagrange Equations, what we could find the derivative of L with respect to z produces this, so dl dz, because our q is z now, produces the derivative of this term. Z dot and z are completely independent, so minus mg, and the derivative of the Lagrangian with respect to z dot produces mz dot, or momentum of the particle, linear momentum. Okay, remember, this is m times velocity. For a non-relativistic particle, mass times velocity is the momentum, the linear momentum. Okay, so as a generalization, let me say it's a generalization. Momentum of a particle for the y component is the derivative of the Lagrangian with respect to the coordinate, to the corresponding coordinate, canonical coordinate. So the z momentum corresponds to mz dot. The component in the x direction would be mx dot here, and so on and so forth. Okay, so with respect to q dot, all right? So this is the general expression for finding the momentum, the momenta of the particle, or the particles, because you can have a set of particles here. But well, if we introduce these things here, what we have in this example, we have dl dz minus the time derivative of dl dz dot needs to be 0. And in this case, it implies minus mg minus the time derivative of z dot equals to 0. The derivative of a derivative is the second order derivative, or z dot dot, which is the acceleration, times the mass. Of course, I cannot forget the mass here, but the mass cancels out here because it appears both terms. And I have z dot dot equals to mg, or g, just g, with a minus sign. Okay? Because I can subtract both sides minus g and change the sign of one of the factors. It's clear here. You can do the math here. Where you have z dot dot equals to minus g. The acceleration of the particle is minus g. It's just because of the coordinate system, which uses a vertical axis pointing upwards, and the gravitational field is minus g in the z direction. It produces an acceleration if you lose the body, if you let the body fall from rest here, or from a specific initial position and velocity, it will satisfy this equation. Of course, there is some constraints here. The initial is z naught, is the initial height of the particle, and the final height, suppose 0. Okay, and you are not interested in what happens here when it touches ground. Okay, so this applies to this motion here from the top to the bottom here. Okay, this is what happens in this case. All right, so I guess you can understand what happens here and an intuitive meaning for the action. Well, for many important physical systems, you need to guess what the Lagrangian is. Okay, and I will let you with exercises for a field phi. Okay, this field phi, it depends for a field phi depending on the coordinate vectors and time t, which usually we just write phi of x using a relativistic notation. X corresponds to x mu, which is equal to x, y, z, and t in Cartesian coordinates. So this corresponds to all the components, but in a very explicit notation, it depends on the position and time, or time and position. It is a field because it's parameterized by the position and time. In relativistic notation, we just write it as x, which contains time and space, or space-time, right? And for this field, suppose there is a Lagrangian density L. I'm writing this L in a different style, okay? And this L depends on the field itself and its derivatives, which we write it the following way, okay? This notation should be clear for those who had a first touch with special relativity, but this means the mu of the field phi, it corresponds to the time derivative. It's a zero component, the time derivative, and the gradient of the field. It depends this way on time derivatives and partial derivatives, x, y, and z derivatives. Okay, so usually this d mu corresponds to first mu runs from 0 to 3 in 4 dimensions. This is time, and this is for space. Okay, mu equals to 0 corresponds to time coordinate. Usually, if you are using physical units in the international system, this x naught corresponds to the velocity of light, the speed of light in vacuum times t. All right, so you need to insert 1 over c here if you are using the SI units, but usually you set c equal to 1 in natural units. And you have d dx1, d dx, sorry, upper indexes, x1, x2, and x3, right? This corresponds to the 4 vector representing the 4 divergence or 4 gradient or so on. Okay, in this case of a scalar field, for instance, d mu phi corresponds to the time derivative and all the components in the space directions. Okay, x1, x2, and x3 would correspond to x, y, and z. All right, and perhaps I will make another video discussing tensors and the main aspects of that. But for now, consider that, okay? D mu of phi, the derivatives, consider all time and space derivatives. Okay, suppose there is a Lagrangian density. The Lagrangian of this field should be, should be a function only of time. So you need to integrate this Lagrangian density with respect to the volume. Okay, so the Lagrangian itself corresponds to an integral over volume. Usually in 3 dimensions, we write it as d3x. This corresponds to d volume, which is dx, dy, dz. Right? You integrate it over all the volume of space, okay, over all the volume of space of the Lagrangian density. Okay, so the Lagrangian corresponds to the volume integral of the Lagrangian density. And of course, in the International System of Units, this is measured in joules per cubic meter if your space is a 3-dimensional space. Of course, if you are dealing with a 2-dimensional situation with respect to space, this could be joules per square meter, or if it is a 1-dimensional problem, it is joules by divided by meter, okay, joules per meter. All right, so this integral in 2 dimensions is dx dy, and in 1 dimension is just dx, okay? But in 3 dimensions, dx dy dz. If you want to insert another space dimensions, you would integrate over dx, dy, dz, dw, for instance, in 4 space dimensions. So the Lagrangian measured in joules, again, corresponds to the integral of the Lagrangian density over the entire volume of space. Okay, so suppose that the action of this situation is an action depending on the field. Of course, the field enters the problem through the Lagrangian density, and the action is an integral, corresponds to an integral over dt prime. Let me write dt prime over d3x prime and the Lagrangian density, which depend on field on the field phi and its partial derivatives. Let me write this primed because I am considering with respect to x prime, z prime, y prime, and so on. The phi field, which is calculated here, this phi field is calculated in the x prime position. So you integrate over the entire space-time volume for finding the action. This is actually the main difference between particles and fields. Now you need to define a Lagrangian density and integrate over the volume, not only over time. And time here, of course, should be from some initial to a final time. And there are constraints. The fields phi naught depending on the position, and the phi final depending on the position corresponding to this first instant of time and this end instant of time are constrained. You have to specify what are the distributions of this field for the initial and final times. So this act as constraints. Okay, this is constrained. The field is constrained. So this, I will call it boundary conditions. Okay, but it's bounded in time. It could be also bounded in space, of course. Okay, so this initial configuration and the final configuration perhaps are constrained, are defined, right? So this is it. Suppose there is a field, there is a Lagrangian density, you can write an action, and the action is constrained by the initial and final distributions of this field. Of course, this A could be written as the following way: an integral over d4x. When this notation is used is because you are considering the hypervolume including space and time components. So this dx4, it is dt prime d3x prime, which is dt dx dy dz prime, of course, of the Lagrangian, and the Lagrangian depending on uh, phi and its derivatives, space-time derivatives. This is the most general, or perhaps for a scalar field, its most general situation which we can have. So this is the action. You need to variate this with respect to the field. Remember, I am using the integral here in the variables x prime, so x prime here, primed derivatives and so on, just because we want to calculate the functional derivative with respect to the field phi evaluated at some x, right? So the exercise is by calculating the functional derivative okay, of A, of the action, which means delta of A depending on the field phi at x prime, which is integrated. X prime comprises the space-time coordinates. You variate that with respect to the field evaluated at some x, which is in the range of these x primes, by calculating the functional derivative of A and equating it to 0, which means calculate this, make it equal to 0, find the Euler-Lagrange equations. Euler-Lagrange's equations. Okay. Whose answer to this problem is the derivative of the Lagrangian density with respect to the field, okay, minus the for divergence of the derivative of the field of the Lagrangian density with respect to the components of space-time derivatives, it should be 0. This is the resulting of equating that to 0. You'll find this. It can be found in any textbook or in many textbooks in quantum field theory. You should find this. And I can recommend, for instance, field quantization by Greiner and Reinhardt. Okay, so you can find out these for fields. Okay, This corresponds, if you open it in terms of all the in a more explicit language, you'll find out that this is equal to dl Lagrangian density with respect to the field minus derivative with respect to time of dl d phi dot usually means in this context time derivative, so dot dl d phi dot minus the divergence of a vector obtained by the derivative of the Lagrangian with respect to the components, which is, for the sake of simplifying notation, is written as the gradient of the field. Okay, but it needs to be understood as dl with respect to d phi dx is one component of this object here. dl with respect to d phi dy is another component, and so on and so forth. So you have inside the Lagrangian space-time derivatives, and of course this is the divergence of this gradient with respect to these components here. This is what this simplified notation means: the time derivative of dl d phi dot minus the divergence of the derivatives of the Lagrangian density with respect to the components of space derivatives, and this is to be equal to 0. Anytime you find out a index being repeated, this mu is repeated here and here, you need to zoom out. So this is d0 dl dd0 plus d1 dl dd1. Of course, in the end there are minus signs here, a minus sign. So minus, minus. And so on. Okay, this means anytime you have a repeated index, you need to use Einstein's convention of summing over repeated index, which means summation over mu from 0 to the number of dimensions of space-time. 0 for time, 1, 2, 3 for the space components. So usually you don't write this summation symbol because of the Einstein convention of summing over dummy indexes or repeated indexes. This index is repeated, you need to sum over all of them. But explicitly, the equation means this. Notice that for a particle, you have the coordinates here. There are only time derivatives for a particle, but for a field, it can vary throughout space. So you need to include this aspect of a field, the space derivatives, in your equations of motion. And the Euler-Lagrange equations produces for you, after you have extremized the action through a certain Lagrangian density, it provides you the equations of motion, the dynamics for that field. Okay? So after you demonstrated this, you can consider another problem, which is find out the equations of motion or the dynamical equations for field phi, which depends on space-time components, coordinates, which is a scalar field in this problem, scalar. If you have a vector field or a spinor field or something else, for each component of the field, the Euler-Lagrange equation must hold, And therefore it is called Euler-Lagrange equations, because if you have multi-component fields or many fields, it could produce a set of coupled equations. Okay, so for a scalar field, you need to calculate the Euler-Lagrange equations. So find out the dynamical equations for the field phi with L given by, suppose, the following: in two dimensions, one for space, one for time. I need to have phi. I need to have time derivative. I need to have a single direction here, x derivative. So this Lagrangian corresponds to d phi dt squared, okay, minus d phi dx squared. Here, of course, if you are trying to use the proper units, use c squared here, or perhaps you need to have some h bars over there, or you need to renormalize the phi's with the proper dimensions. But this field here, and I can also introduce some, suppose, some constant. Let me call it m squared times phi squared. Suppose this is the field I am trying to calculate the derivatives and find out the dynamical equations. So it's pretty easy to do that. If I'm calculating dl d phi, I will produce a factor minus m squared. It is to be divided all the factors by 2. So all this equation divided by 2. Okay, m squared over 2, 1 over 2, 1 over 2, everything divided by 2, because when you calculate the derivatives, this cancels out. It's better to do that. So minus m squared, if I am calculating the derivative of the field of the Lagrangian density with respect to the field. The only factor which depends on the field is this one. I'm calculating the derivative, a factor of 2 appears, which cancels this one. Okay, so minus m squared phi. If I calculate the derivative with respect to phi dot, which is the time derivative, this is, by analogy, the canonically conjugated momenta of the field, or momentum in this case for a scalar field, momentum of the field, or canonical momentum. Okay, and in this case, what I have is this factor which depends on phi dot. A factor of 2 appears. I am dividing by c squared, so I have d phi dt. This is the canonically conjugated momenta, or momentum, because in this case it is a singular, but for other fields, perhaps multi-component fields, you need to calculate with respect to some subindex here, so you find out a component of the canonical momentum of the field. All right, but in this case, no problem. And of course, I need to calculate dl d phi dx. This is to be understood as the variable. Okay, so calculate the derivative of the Lagrangian density with respect to this derivative here, and it produces a minus a factor of 2, which cancels the other 2 there, d phi dx. Okay, this is the variable. D phi dx is a variable, and you are calculating the derivative of the Lagrangian density with respect to this variable. This doesn't depend on d phi dx. This depends, it's a quadratic function on d phi dx, and this doesn't depend on d phi dx, it depends on phi. So this is independent. The derivative is 0 with respect to this term here. This corresponds to a factor of 2. This minus is present, so I need to carry it together. Minus d phi dx. Okay. I calculated all the required derivatives. Now I need to insert into the Euler-Lagrange equations, which produces the following in case of only one space coordinate. I need to make it equal to 0. I don't know if it's clear what I'm writing here, okay? But I guess it is. So our equation of motion will be given by, let me see, dl d phi, so minus m squared phi, the first term, which corresponds to this, minus the time derivative of the canonical momentum here, and the time derivative of a time derivative corresponds to a second order time derivative, so minus 1 over c squared, second order time derivative, minus 1 over c squared d phi dt2, and this minus cancels that one. The derivative with respect to x of a first derivative becomes a second order derivative, but there is a minus sign coming from here, which cancels out this one. So plus second order phi, second order derivative with respect to x of phi, and this is equal to 0. Okay. So this is it. This is a wave equation with a parameter m squared here. Some factor, I don't remember if I put this sign correctly. Perhaps it's a plus, but it doesn't matter because what I'm trying to calculate here or to demonstrate here is the procedure. So if you have a minus here, it doesn't matter. In your equation, it will appear a minus factor, but it should be corresponding to a mass factor for a field. So for fields, we have a velocity factor, a spatial derivative factors, and some potential, some mass perhaps, and so on. Okay. If m equals to 0, this is just a wave equation in one dimension. So if you are trying to calculate or trying to find out what is a Lagrangian density for a scalar field satisfying a wave equation, it corresponds to just these two factors here. It's massless field. This term disappears. So there is no such factor. This term here disappears. You'll have a wave equation. If you have a more dimensions, what you need to include is minus d phi dy squared minus d phi dz squared, which is usually written, now try to demonstrate that, usually written the following way. For a scalar field, Lagrangian could be written this way: d mu phi and upper index d mu phi. 1 over 2, 1/2 of that, and this corresponds exactly to 1/2 of the time derivative. I'm using c equals to 1 now, minus 1/2 of the gradient of the field squared in modulus. Okay. This gradient squared. This represents, as a matter of fact, gradient of phi dot gradient of phi. You write this as gradient squared. Okay, so d mu corresponds to time derivative and the gradient, and the upper index you need to change it by using the metric tensor, to raise up this index, the nu, and it corresponds to time derivative minus the gradient. Okay, the time component is ddt, but the space components reverse sign, switch signs. In some convention of the metric tensor, which is just a diagonal matrix comprising or composed by one in the diagonal, but space components are -1, and conversion of time components +1. So you have a matrix like that. 1 0 is missing here. Okay, something like that. All right. So this is it. This is for a scalar field. This is the Lagrangian. You can use the Euler-Lagrange equation. You saw, or perhaps I guess we could discuss a little bit in terms of more intuitive aspects. What is the functional derivative? What is the action principle? And next time we can discuss another problems. I hope you enjoy it. I hope it's useful. See you next time.